Hello and welcome everyone to week 4 of the tutorial session for the course of Secure Computation 2. So, as usual, I will just quickly recapitulate the concepts of week 3 once, then we will take a look at week 3 assignments and their corresponding solutions, and then we will take a look at the contents of week 4. Okay, so let's proceed. So I will be sharing my screen and then we will discuss. I hope my screen is visible. Okay. So to begin with, we will take a look back at week 3 topics, right? So also just to take look even before that, so we are dealing with protocols in the multi-party setting, and where the adversaries can behave maliciously, that is they can deviate from the protocol in an arbitrary fashion. So we have in the week 1 we got introduced to Byzantine agreement and reliable broadcast protocol. We also got introduced to the exponential information graph protocol, EIG protocol, for perfectly secure BA, right? Perfectly secure BA. And we also saw its corresponding analysis, where we discussed that for any Byzantine agreement or reliable broadcast protocol, the three necessary properties are liveness, consistency and validity. And after that we had seen the proof of validity, consistency and liveness for EIG protocol, and then we had seen the Phase-King 1 protocol, right? Phase-King 1 protocol for perfectly secure Byzantine agreement. However, in EIG protocol, our communication complexity was exponential, that is of the order of n to the power t plus 1, right, where n is the total number of parties and t is the number of corruption tolerated at most, right? So t is the maximum number of parties that can be corrupted among n parties, right? And all these corruptions we are talking about are Byzantine corruption, right? Okay. Now in case of Phase-King 1, we reduced the communication complexity quite a lot, from exponential to polynomial. So in Phase-King 1 protocol we required almost order of n cube communication complexity, right? And but in case of EIG protocol, so if I just briefly write that communication complexity and the tolerated corruption threshold, in other words, right? So in case of EIG protocol it was almost order of n to the power t plus 1, whereas corruption, right, was less than n by 3. In case of Phase-King 1 protocol, we improved over the communication complexity, which was almost order of n cube, whereas tolerated corruption was lesser, so it had to be less than n by 4. And then we saw another protocol called phase-king 2 protocol, right? There again the communication complexity was of the same order, but the threshold corruption or corruption threshold again got improved to t less than n by 3, right? Now we also had, so all these three protocols were bit BA protocol, right? So all the parties have a single input bit, and then after running the Byzantine agreement protocol, all the honest party would agree upon a common output bit. That is the purpose of this Byzantine agreement protocol. Also we had seen that all these Byzantine agreement protocol can be converted to reliable broadcast protocol, right, with the same constant as of BA, right? So this corruption threshold will remain same when we convert these bit Byzantine agreement protocols to bit reliable broadcast protocol, right? So all this conversion procedure was discussed in week 1. Then in week 3, okay, so before that we had also seen this domain extension, right? So we had also seen domain extension. In particular we saw the scheme Turpin Cone domain extension protocol, where we convert a bit Byzantine agreement protocol to L bit Byzantine agreement protocol, that is each of the party will have a L bit input, right? So this domain extension can be equally applicable for reliable broadcast as well, right? Okay, now after that in week 3, also another thing, all these protocols are, these three EIG protocol, phase-king 1, phase-king 2, all of them are perfectly secure, right? So what do we mean by perfectly secure BA protocol or RB protocol? There we are dealing with computationally unbounded adversary, right? So the adversary has unbounded computational power, computationally unbounded adversary, and all three security properties, right, namely validity, consistency, and liveness or termination, all of them are satisfied with probability 1. Okay, right. So that is what we mean by perfectly secure. Now in week 3 we actually saw a protocol called Dolev-Strong protocol for reliable broadcast, right? So this protocol description was for reliable broadcast, which can obviously be converted to a BA protocol. However, the restriction here, okay, if we talk about corruption threshold, it is just t less than n. So for any t less than n, basically the maximum or so at most n minus 1 parties out of n parties can be corrupt in the Dolev-Strong RB protocol, but when we convert the same protocol to a corresponding Byzantine agreement protocol, then our corruption threshold will change to T less than n by 2. So honest majority will be required if we want to design Byzantine agreement protocol from this existing reliable broadcast protocol. And why this condition comes to play, that we had seen when in week 1 we described the protocol for converting any RP protocol to BA protocol. We had seen that why this honest majority setting is required while converting. Okay. But one thing to remember is that for this RP protocol only T less than n will suffice. Also, another property for this Dole-Armstrong protocol which makes it different from the previous protocol is that it is cryptographically secure, right? So this scheme is cryptographically secure. So it is not perfectly secure, right? So in cryptographically secure scheme, we basically in cryptographically secure scheme, adversary has bounded, more particularly polynomially bounded computational power. Okay. And the three security properties are satisfied except with negligible probability. What does that mean? So there is a negligible probability in which case some of these security properties may not hold. So in case of perfectly secure, all these three security property will always hold even against computationally unbounded adversary. So this is a stronger adversary. But here adversary has bounded computational power, so adversary is weaker in the cryptographically secure case, and there is also a negligible probability with which some of the security property may fail, right? So that is cryptographically secure. So this Dole-Armstrong protocol, as you can see, it tolerates a larger corruption threshold. Any T less than n will be sufficient for this protocol to work, but this does not give us a perfectly secure protocol. It just gives us cryptographically secure protocol. And for implementing this, we basically use this Dole-Armstrong protocol uses a digital signature scheme. Uses a digital signature scheme as an underlying building block. And as you know that any digital signature scheme is a basically cryptographic primitive, so there comes the question of cryptographic security, right, instead of perfect security. However, they also mention another variant of digital signature scheme which can give us statistical security or information theory security, where the adversary will have unbounded computational power, but still there is a negligible probability of failure. We call it pseudo signature, but for now, so we just recall the Dole-Armstrong protocol in the context of using digital signature scheme as underlying building block, and how the Dole-Armstrong protocol for reliable broadcast works. We will have a quick look at that. So basically what happens in the protocol, as you know, in any reliable broadcast protocol there is a designated sender, and it wishes that at the end of the protocol, what we really want to achieve is that at the end of the protocol, all the honest party will have a common output. And by the validity property of reliable broadcast, if the sender, the designated sender of RB protocol is honest, then at the end of the RB protocol, all the honest party should have the input of the sender only as the common output, right? And the consistency property ensures that even if the sender is dishonest, so we do not care about what was the exact input of the sender in the beginning of the protocol, but still at the end of the protocol, all the honest parties should agree upon a common output, right? It may not be same as the sender's input, because sender's input can vary to different party because it is a dishonest entity. So by consistency, even if the sender is dishonest, all the honest party will have a common output at the end of the reliable broadcast. Okay. Now in Dole-Armstrong protocol, how the protocol works? So there is a setup phase in the protocol. So in the setup phase, basically, in the setup phase, all PI, so all the party from P1 to Pn, all PI are initialized with their corresponding signing key and verification key. With SKI is the signing key and corresponding verification key VKI, and these are public. All the verification key for all N parties are public, but the signing keys is secret to parties, right? Now in round 0, let me write, in round 0, the designated sender, right, designated sender sends its input M and its own sign. Say if I denote the sender with capital S, so this S is any one party among P1 to Pn, so I am writing it with sender S. So the SK of party S, signing key of party S, will be used to sign this message M. So this input will be sent to everyone. Now if the sender S is indeed an honest party, then it will send identical copy of M comma sign on M with SKS to every other party. But if S is dishonest, then it may choose to send some M1 and sign on M1 by SKS to say party 1, but M2 comma sign on M2 with respect to SKS to P2, and so on. So different party may get different version of message at the end of round 0, okay, depending on whether the sender is honest or dishonest. Now we will run the protocol for round 1 to round T plus 1, right? Now in each round, from round 1 to round T plus 1, everyone receives some information of this form. So each party receives various message of this form. So this is a message mi and its corresponding signatures by several parties. So if skj denotes the signing key of party pj, so mi is signed by several parties. So it may happen that the message mi has been received from party p1, let's say. Okay, so some party pi is receiving a message m1 with corresponding signs. So the list, so this is basically a list of signatures on message say m1 by several parties, okay, in the system. So in this form, each party may receive several message and its corresponding list of signatures. Okay, so once this is received by a particular party, so I am denoting this with mk because I am writing each party to be pi. So I is the index for denoting a party, k is the index for denoting a particular message m, and skj denotes the party who has a signed on some message mk corresponding to party pj. Well, now after this receiving is complete, party pi checks. So pi checks if some message mk has at least r signatures. So we are denoting some round r in 1 to t plus 1, right? So round number 1 to round number t plus 1, the iteration will go on, and any round r among them. So in rth round, party pi checks if some message mk has at least r different signatures on it, including the designated sender signature, that is SS signature, right? So if mk, as I already said that for each message received there is a list of signatures corresponding to it, right? And if some message has been received in rth round with at least r different signatures on it, including the sender signature, then pi appends this mk to the accumulator list, right? Accumulator list, say denoted with ACCI. So of course initially, before the beginning of round 1, this accumulator I is equal to null set for each party pi, and then gradually they will fill up accumulator I according to this policy. And when, so if mk is accumulated in ACCI, right, in ACCI for the first time, right, then it sends again mk comma whatever was received previously r party's signature on mk, all this set appended with its own signature. So sign ski party i's own signature on this message mk to all. So this will be broadcast to everyone. Again, if pi is honest, then identical copy of this thing will be communicated to everyone. Otherwise this can contain any message and its corresponding signature. So you cannot control malicious parties behavior. So basically from round 1 to round t+1, each round r has this receive operation by each party, then this check and accumulating the accumulator ACCI accordingly, and then depending on whether mk is being accumulated for the first time, it will send some message, otherwise it will not send anything. So this is what is done in each round between round 1 to round t+1. But at the end of round t+1, we expect that the common output is established as expected in a reliable broadcast protocol. Okay, and we had also seen that how the consistency and validity of reliable broadcast protocol is maintained here. Right. So when we will solve the assignment question for week 3, we will again take a look at how the consistency or validity is affected in this case. Okay. So before going to the assignment question, we will also take a quick look at the randomized Byzantine agreement protocol. Right. So as I was mentioning in week 3, right, so in week 3 this was one topic, Dole-Armstrong protocol for reliable broadcast, which is a cryptographically secure protocol with t less than n. Apart from that, there was also mention of a randomized Byzantine agreement protocol. Again, we are not in perfectly secure domain, right? So EIG protocol, phase king 1 and phase king 2, all these were perfectly secure protocol. But then in Dole-Armstrong protocol, we had seen it is just a cryptographically secure protocol, not perfectly secure. Now in randomized BA protocol, this is also, it is randomized, so it's not deterministic. Its runtime is expected to have constant round, so constant runtime, but in some cases with some probability it may even run for infinite amount of time. So it is not clearly perfectly secure, but what is the improvement here? It has with expected constant number of rounds, expected constant number of rounds. So if you remember, in EIG protocol we had a EIG tree that had label t+2, so it had to run the rounds or iterations for t+1 times. In phase king 1, phase king 2 protocol also we had to iterate the protocol for t+1 times, and in each of the t+1 phases there were 2 rounds or 3 rounds. In phase king 1 protocol, each of the t+1 phases had 2 rounds. In phase king 2 protocol, each of the t+1 phases had 3 rounds. Coming to Dole-Armstrong protocol also, as we already had seen, that round 1 to round t+1 we need to run the protocol. So t+1 number of rounds are there, but coming to, so all this, in all these cases the number of rounds required or the communication complexity is depending upon the corruption threshold T, right? However, coming to randomized PA protocol, which is not perfectly secure protocol, we are able to achieve constant number of rounds, right? So again this is with n greater than 3t, and our expected number of rounds is a constant, which we in the protocol it was shown by mathematical derivation that the constant is actually 9. So it is expected that your protocol will finish within 9 rounds with a high probability, or with like expected number of rounds. Okay, expected 9 number of rounds. So what was the randomized BA protocol that we had described? Just take a quick look at that. So randomized BA protocol. Here we have two building blocks. One is vote protocol. So what is vote protocol? So this is a 1 round protocol where again n is total number of parties, t is corruption threshold, and what do you expect from the protocol? So this protocol, I can say, ensures this protocol ensures validity, which means if all the honest party have same input in the beginning of vote protocol, they will retain that same input at the end of vote protocol, right? So it is valid, right? However, in terms of consistency, it is almost consistent, which means, so I can write this protocol ensures almost consistency. So to elaborate, validity will imply that if all honest parties have same input bit B in the beginning of vote protocol, then at the end all of them retain B as the output. And for almost consistency, what I mean is that if an honest party outputs a bit B, then other honest parties must output B or bot. So if all honest parties must output B, if that is the case, then it would have been completely consistent protocol. But since if one honest party outputs bit B, other honest party must output either B or bot, then it is almost consistent. So if it would have been the case that some honest party outputs a bit B and other honest party may also output bit 1 minus B, that is complement of B, then it would not have been a consistent protocol. But since at least this much is ensured, that either a honest party outputs some bit B or the bot, okay, but there is no inconsistency that one honest party outputs B but another honest party outputs B complement, nothing like that occurs. So it is almost inconsistent. Okay. Now this is about vote protocol. Now how the vote protocol was instantiated, basically if you remember, this is just one round protocol. All the parties have some initial input, say Bi, right? So the protocol description is this, that each Pi initially has input Bi, it broadcasts Bi to all. So this send operation is completed. Now each Pi receives some bit from all the parties. If a bit B is received at least n minus t times, right, then you will assign your next Bi to be that bit only, right? Then Bi is B, else Bi is bot. Okay, that much only the vote protocol. Now comes the coin protocol. So in the coin protocol, this is again a one round protocol, and there is no input to the parties. So it is like some internal coin toss is happening inside each party. How exactly that random coin output is generated, that is part of the instantiation of coin protocol. But overall, the coin protocol ensures, so the coin protocol ensures that all honest parties have a common random output with some probability p. Otherwise you cannot comment on the output of honest parties, but with probability p you can always say that all the honest party have a common random output, which is unlike the case of vote protocol. In vote protocol, only if all the honest party are starting with the same input, then it is always ensured that that input will be written at the end of the protocol. But uh, otherwise all the honest party will have either B or bot. But in coin protocol with probability P, all the honest party will always have a common output, which is of course random. Okay, right. Now overall, so we will come to the instantiation of coin protocol. But before that, how the overall randomized BA works. So there is one round of vote protocol, at the end of which, so let's say parties are starting with B1, B2 to Bn. At the end of first round vote protocol, the honest party will have either B or bot, right? And then the coin protocol does not take any input to it, but at the end of coin protocol all the bit of honest party will be same irrespective of their initial input. So all of them will have a same common output C with probability P. Okay. Now there will be another round of vote protocol where the input will be, so if the output of vote protocol, output of first vote protocol was bit B, then the input will be bit B. But if the output of first round vote protocol was bot, then input will be the output of coin protocol, and so on. Now you can see that this random coin output C will be equal to B. So the probability that the random output C is equal to actually the bit B, which the honest parties are almost agreeing upon, that probability is half. So overall we say that at the end of one iteration with probability P by 2, all of the parties will have the same common output. So then again the next iteration starts. So this is one single iteration, and this protocol goes on until all the honest parties are on the same page. And there is an improved version of vote protocol called the Greatcast protocol, where we also accompany the vote protocol output with some confidence value, grade 1, grade 2, etc. So that when some parties gets a particular output at the end of vote protocol with sufficient confidence, then they can exit the protocol while raising a special halting signal to say that from next round onwards you can consider this bit value as my contribution to the input, but I am exiting the loop. Okay. So that is about overall randomized PA protocol. And inside the coin protocol is instantiated with the help of digital signature scheme. So in the coin protocol, basically each party sends some value vi consisting of its own party ID, some random publicly known random string r, k is the iteration number, so this is one particular iteration, right? So in the ith iteration, when the coin protocol is being run, that will take I, so at kth iteration the coin protocol inside kth iteration will take this value as k and then sign on these values. Okay. This is sent to everyone. Now since pi is a publicly known value of the sender, so each party when receives some value vi from a party pi, it checks whether the first entry is indeed pi, second entry is indeed the publicly known string r, k is indeed the correct iteration round. All these can be publicly verified. And also since the verification key vki corresponding to the signing key ski of party pi is available to everyone in the public, this sign can be verified by any party with the key vki, verification key vki. So the vi, basically vi can be verified publicly, in short. Now whenever you have received a correct vi value, then each party, after receiving all the vi's from other party, after receiving the vi's, computes a hash value on each of these vi's, right? Or I should write receiving vj's. So pi is receiving all the vj's, and then it computes h of vj for all, right? j equal to 1 to n, whichever is received and verified successfully. For them all the hash values are computed, and the minimum hash value, so if party pm has least value of h of vm, right, then the point protocol output is h of vm, right? Okay, so that is all about the randomized PA protocol, and we had seen that after the application of proper modified port protocol or gatecast protocol, we can achieve a expected constant round number 9 for the randomized PA protocol. Now we will take a look at the assignment question. So first question is, choose the correct statement from the following based on modifications made to Dolive-Strong protocol for reliable broadcast. Modification 1, in round R, accumulate value V if at least R parties have signed V, irrespective of whether S has signed V. So in this modification, so as we already mentioned while discussing Dolive-Strong protocol, that in each round R, the party checks if some message MK has been received from R distinct parties with their signatures, including the sender S's signature, right? But what if this check whether the R distinct signatures on message MK includes the sender S's signature or not? If that check is not there, then what will happen to the correctness of the protocol, or in short, to the consistency or validity of the protocol? So our claim is here that this modification 1 will actually affect the validity. So validity will not be satisfied. How? So you can imagine the scenario that sender S, also remember any number of parties can be corrupt, right? So let's say in one protocol there is P1, P2, P3 and P4. P4 is the sender, let's say, and say this is honest, P4 is honest, and P2 is a corrupt party, as you know. Okay, so what happens? P4 has the message in to send to everyone. Okay, P4 can send M with corresponding signature on M, right? However, P2 being a corrupt party, it can do anything, right? So it also sends some M dash with its own sign, right, on M dash. So in the view of P1, during round 1, it has received two messages, each with one signature on them. So M at the round 1, M also has signature on it, one signature on it. M dash also has one signature on it. So P1 basically will have both M and M dash to its accumulator list, right? Same goes for P3. So P3 will also, after receiving such content from the corrupt party P2, it will also have both M and M dash inside its list, and P4 also will have both M and M dash to its accumulator list, and as a result some default value will be output, because the output of Dole-Armstrong reliable broadcast protocol is equal to the content of the accumulator only if the accumulator is a singleton set, otherwise it outputs some default value. Now in this case, the accumulator for all the honest party P1, P3 or P4, they are not singleton set, so they will output some default value. However, in this case the expectation was that the output should be M, because our sender was honest and it had started with initial input M. So it is expected by the validity of the property that all the honest party at the end of the protocol will output the value M only. But instead of that, it happens that because we did not check whether the message M dash had included the sender's signature or not, that check was not there, and as a consequence we see that the validity property is not satisfied. So modification 1 affects validity. Then there is modification 2 as well. So modification 2 says run the protocol for r equal to 1 to t rounds. So what if instead of t plus 1 round as mentioned in the original protocol, we run the Dole-Armstrong protocol for only t rounds? So if you remember, when we discussed the consistency property of Dole-Armstrong protocol, we in the proof we had shown that at the end of t plus 1th round, if some honest party Pi has a value V in its accumulator list, then there must be presence of V in accumulator of some other honest party Pj as well, or in other words, the content of accumulator will be same for all the honest parties. And why is it so? Because after the completion of t plus 1 rounds, there must be one particular round where this value V was signed by some honest party, right? And some honest party must have signed, because there are at most t corruption. So if some message has been signed by t plus 1 parties, then there must be one party among the t plus 1 parties who have signed the message V, and if that is the case, that party must have broadcast the message to all the parties honestly in the next round, of course. So that's why if value v is present in accumulator list of honest party pi, value v must be present in the accumulator list of honest party pj. But if you cut down the number of rounds, the same argument will not hold anymore. So modification 2 will affect consistency. This is the next question. Consider the common coin protocol discussed in the lecture. Match the following adversarial attacks to the reason why the attack fails. So first attack is product party pi chooses vi such that hash value of vi is the smallest value in the range of h. Now h is basically a hash function modeled as random walking. What do we mean by that? So h is a hash function modeled as random walking. That means for any new input x, right, h of x is random, right? That is the assumption when we are claiming h to be random oracle. Then for any new x, h of x is random, and by the property of hash function, one cannot get the pre-image x by looking at h of x. This is the property of hash function. Now simply, if one even wishes to choose vi in such a way h of vi is the smallest, it cannot do that, because by instantiating h of vi first, one cannot get back a valid vi. That is prohibited by the security of cryptographic hash function. So the answer is h is assumed to be a random function and so difficult to invert. So 1 goes with C. What about second option? Product party pi waits to receive vj from all honest parties pj and sets vi to the smallest value among these. Now if one party even wants to do that, right, so you know the pi content is basically the party id pi, the common string r, publicly known common string r, the iteration id k, and its sign on the value of r and k by the sending party. Now if one party wants to replace its own vi to the content of some other party's vj, then it must fail the verification, right? So it will not work, this strategy will not work. So 2 corresponds to A. And finally, if a corrupt pi gets selected in some random iteration, pi is likely to get selected in the random next iteration as well. This does not hold true, because again h is a function modeled as hash function modeled as random oracle. So as we have seen that if in some iteration pi has value, so pi is pi comma r comma k and sign on r and k, then in the next round what is the value for pi? In the next round value becomes pi comma r comma k plus 1 in the next iteration, and sign ski r comma ki. Now so let me denote it with vi dash in the next iteration. Now h of vi and h of vi prime is completely basically they are not at all related. So although Vi and Vi dash, although Vi and Vi dash have some similarity in the string, input string, but due to this small change k and k plus 1, and also this signature will be different for different values. So this is r k plus 1. For the small change in the input value of hash function, the output value of hash function will be completely random. So it does not matter, or it does not affect the thing that if Pi was selected as the party having least hash function output value, it is rarely possible that in the next iteration also the corresponding hash function output value will be minimum of all, right, in the next iteration. So our answer is basically 1C, 2A and 3B. That is, with small change in input there is a large change in the output of each. Okay. So last option is the correct option. Consider the randomized BA protocol discussed in the lecture without any halting criteria. Run for k equal to 100 rounds and the modified version with halting okay. So choose the correct option regarding communication complexity. Expected reduction of a factor 0.0081 in communication complexity using the modified version. Definite reduction of a factor 0.0081 in communication complexity using the modified version. Expected reduction of a factor 0.09 in the communication complexity using the modified version. No definite reduction in communication complexity using the modified version. And so in the first version, where it was just vote, coin, vote and reiterate, if that protocol was run for 100 times, on the other hand our modified protocol, that is gradcast, coin, gradcast and reiterate with halting criteria, right. Halting criteria was that if some bit B has been received from n minus t parties, then we would output B with confidence 2, right, gate 2, and the party will exit the protocol basically. So using that criteria, we had seen that expected number of iteration was 9. So clearly here you are doing 100 iterations and here your expected number of iteration is 9. So you reduce the expected reduction, you reduce the expected communication complexity to a factor of 0.09, right. So this is correct. And no definite reduction in communication complexity using the modified version. This is also true because 9 is the expected number of iteration, but it may be the case for a particular instance the protocol goes on and on and on, so you cannot comment on definite reduction, it's just expected reduction. So the last statement is also true, which says that no definite reduction in communication complexity using the modified version. Consider the following randomized protocol for Byzantine broadcast. So Byzantine broadcast means reliable broadcast. So randomized protocol for reliable broadcast for 3t less than n, where sender S wants to send input bit B to all honest parties in party set B. Okay. So each party Pi except S initializes sticky bit Pi to bot. S initializes Pi to B. So at first every party except the sender initializes its own bit Pi to bot, and sender S initializes Bi to bit B, its input B. Then each party initializes a leader LR for each iteration R. For the first iteration L1 is A. For the first iteration L1 is S. So round 1, then leader L1 for round 1 is S. Otherwise LR is randomly chosen from P using an oracle, and all party will get same leader chosen in every iteration. Okay. So for round 1 the leader is fixed, it will be the sender, and other than that for all other iterations the leader will be chosen randomly by all the parties. Then for iteration r equal to 1 to k, okay, so there are k iterations and each iteration has 3 rounds. We can see round 1 says that if LR's sticky bit is not bought, so leader's sticky bit is not bought, then leader sends its sticky bit to all parties. Otherwise leader randomly chooses a bit and sends to all parties. So if it is not bought, that means LR has a valid input to it and it then sends this input bit to all the parties. Otherwise if its input is actually bought, then it randomly chooses a bit and then sends it to all parties. So in round 1 only the leader LR is the sender and all the parties are receiver. In round 2, suppose party Pi receives B from LR. If Vi is bought, that is Pi's own input is bought, then it sends B to all parties, else it says Vi to all parties. So B is the bit received from leader and Vi is its own bit. So only if its own bit is bought, then Pi sends the leader's bit B to all parties. Otherwise it sends its own input to all parties. Then in round 3, so notice that in round 2 all the parties act as a sender. In round 1 only leader acts as a sender, all other parties are receiver. In round 2 all the parties act as sender and all the parties act as receiver as well. In round 3, if party Pi receives some bit B from n-t parties, set Vi to B, else set Vi to bot. Okay. So here there is some majority concept that it will set Vi to a particular bit only if that bit has been received by from at least n-t parties, that is with sufficient confidence. Otherwise Vi is beta for the next iteration. Okay, that is the description of a protocol. Now the options are: it is not possible for two honest parties Pi and Pj to set sticky bits Vi and Vj such that Vi not equal to Vj and both Vi and Vj are not bought. So it is saying that whether the protocol satisfies the almost consistency or not. So almost consistency says that if some honest Pi has a bit Pi, then no other honest party should have output, should have Vi complement as the output. So either they will have Vi only or they will have bot, right? So let's see. In round 3, just looking at the last round of each iteration, let's say party Pi has received B from n minus t parties. Okay. We will check whether it is possible for some other honest party Pj to receive or to assign B complement as Vj. Right? For party Pi, Vi is equal to B. Whether it is possible for some other honest Pj to have Vj equal to B complement. We will check that. So, according to our already known techniques, let's verify that Pi has received bit B by n minus t parties. Out of them, there can be t parties which are corrupt and n minus 2t parties which are honest. These corrupt t parties may send B complement to other honest party Pj, and outside the set of n minus t parties there can be another t parties who are honest and who genuinely send B prime as their corresponding bit to Pj. Now in total Pj receives 2t number of copies of B complement. Now is this a sufficient number so that Vj is equal to B complement? For that we need 2t should be greater equal to n minus t. That means n should be less equal to 3t. However, this is not the case. So the cutoff criteria for having Vj equal to B complement is not satisfied. So Pj, that is any other honest party, will never assign B complement as their Vj. So it will be either B or bot. So this statement is true. The next statement says that if some honest party Pi sets Vi to B in iteration R, then every honest party Pj sets Vj to B in iteration R plus 1. Now let's see. Some honest party Pi sets Vi to B in iteration R. That means all the other honest Pj has set Vj equal to B or bot in iteration R. That is implied by the previous statement. Right? So in the beginning of iteration R plus 1, all the honest party have input either B or bot. Now what happens after the end of iteration R plus 1? So let's see how the protocol proceeds. So in each iteration, at first some leader is chosen, right, randomly. Now it can be the case that some party with input B is chosen as leader, or it can be the case some party with input bot has been chosen as the leader. Okay. Now for the first case, that some party with input B has been chosen as the leader, then it will send bit B to all the parties, and okay, now okay, let's proceed with the second case where the leader has been chosen to be a party that has bot as the input. In that case, that party will randomly choose a bit B. So that bit can be either equal to B or equal to B complement. Let's say it chooses B complement. Now it will distribute B complement to all the parties, and suppose Pi receives some bit from LR, so each party will receive, since we are assuming Pj to be a honest party, here the leader party to be honest, then everyone receives B complement from the leader party. Now only the parties which had B as their corresponding VI previously, they will broadcast B to all the parties, and the parties that had bought previously will broadcast B complement as their corresponding VI to all the parties. So clearly there is no such majority. Okay, we cannot guarantee the majority. So the statement that at the end of R plus 1th iteration all the party will have bit B as their corresponding output is not true, right? You cannot comment on that. Okay, so this statement is not true. In the third statement, if an honest party is chosen to be the leader for iteration R, then all honest parties will have the same sticky bit at the end of the iteration. So we already just discussed that even if some honest party is chosen to be the leader for iteration R, it can just from the previous round it may have only bought as its corresponding bit, so it will randomly choose a bit 0 or 1 which so basically just due to the previous statement, analogous to the previous statement, we cannot ensure that all the honest party will have the same bit B at the end of the iteration, even if the leader is honest. We cannot guarantee that. The fourth statement says if an honest party is chosen to be the leader for iteration R, then all honest parties will have the same sticky bit at the end of the iteration with probability at least half. This is correct because if the honest party chosen to be the leader for iteration R, that party may choose the same bit B as of the other honest parties and broadcast it. In that case, all the honest party will have the same bit at the end of the iteration. And the fact that random coin toss will give you the same bit as of the other honest parties, that has probability half. So last statement is correct. Choose the correct option from the following in the context of cryptographically secure Byzantine agreement and broadcast protocols. Digital signature alone can be used to set up private and authenticated channels. Okay, so digital signature is just to ensure authenticity of a message, right? But it does not do anything about privacy. In standard cryptography, you use encryption scheme for ensuring privacy of the message, and you use signature scheme for authenticity of the message. So clearly the second option is the only correct option, which says that digital signature alone can be used to set up authenticated channels. Okay. So we are done with the week 3 assignment discussion. Now we will quickly take a look at the week 4 content. So the week 4 contents are starting with the formal proof on the lower bound on corruption threshold. So in any, so we already had seen it as a required condition that for any perfectly secured Byzantine agreement protocol, needs n to be at least thrice of the corruption threshold. But why so? Okay, why so? So that thing has been proven formally in week 4 content. So at first we see that it is not possible to have pi 3ba where n is 3, t is 1 for perfectly secure 3-party BA protocol with at most one corruption, right? And to show that, we had a quite involved proof which shows that there is a system of 6 entities. Okay, so basically the proof proceeds with contradiction. So the proof is that we assume such pi 3ba exists, then a system S of 6 entities with no corruption is expected to have well defined outputs, but that is not the case. Hence we conclude pi 3ba does not exist, right? And then we again formally prove that it is not possible to have pi 3t, so n equal to 3. Perfectly secure n-party BA protocol with T Byzantine corruptions. And the proof again proceeds by contradiction. So first we assume such pi 3t exists, then we derive a pi 3ba from pi 3t using player partition technique, right? Okay. However, we already know does not exist, we conclude pi 53 can't exist, right? So with this, so till now, till this point, for all the protocols, say starting from EIG, phase king 1, phase king 2, Doleb-Strong or randomized BA, everywhere we assume pairwise secure channel among n parties. Next, they talk about perfectly secure BA for n parties connected by an incomplete graph. So if pairwise secure channel exists for all the parties, then that is basically a complete graph. But what if parties are connected by some incomplete graph? Then what is the condition for achieving perfectly secure BA? Now, as we have seen in the lecture, that the conditions are, first is of course n greater than 3t, because otherwise if we would have been able to achieve a perfectly secure Byzantine agreement protocol for incomplete graph on n parties with n less equal to 3t, then we must have been succeeded to design perfectly secure Byzantine agreement protocol for complete graph as well. But that is not the case. So it is again a necessary condition for perfectly secure BA on an incomplete graph as well. Apart from that, one extra restriction is that vertex connectivity of the graph should be at least 2t plus 1. Okay. So concept is basically this: even when you do not have, say, you have a sender and you have a receiver. So when in complete graph you would always have a secure channel between S to R, but in absence of that, you must have some vertex disjoint path from S to R. So even if, so let's assume there are 3 paths. Vertex disjoint means no 2 paths should contain a common vertex. Otherwise, if that common vertex is compromised by the adversary, then that would affect the other paths containing that node also. So we just focus on vertex disjoint paths between S and R, and let's say such 3 paths exist and one Byzantine corruption is allowed. Then if sender sends the same value through all these 3 wires, so here 3 is 2 into 1 plus 1, satisfying the formula of 3t plus 1 basically. So if that is the case, then all the vertex will send the value m to the receiver R through all the available 2t plus 1 paths, and then receiver will take decision on the received value depending on what is the majority value that is received through the 2t plus 1 wires. And since at most t wire can be under adversarial control, t plus 1 wire at least will be free from adversarial control. And since t plus 1 is greater than t, the majority of the received value will be retrieved by the receiver R. So even if 1 is corrupted, 2 copies of M are still visible to R, and R will retrieve M as the correct message. Okay. So it is intuitively quite clear that why you need. So just to mention that what is vertex connectivity for a graph, if you need to delete at least k number nodes of the graph to make it a disjoint graph, or to extract a single node out of that graph. Okay, so that means even if you remove k minus 1 node, till the graph remains connected, but after removing k nodes, the graph becomes disconnected graph. Okay, so that is what we mean by vertex connectivity. And then by this particular illustration, it is clear that why it is required at least 2t plus 1 number of disjoint paths to exist between any two nodes in a graph. And so for any incomplete graph, if this much condition is satisfied, that vertex connectivity is 2t plus 1, then it is possible to design a perfectly secure Byzantine agreement for n parties according to any existing protocol that we have already discussed for Byzantine. Whenever there is a need for communication between party Pi to party Pj, if an edge exists between Pi and Pj, you send the message through that channel only. And if that does not happen, so if there is no direct edge from Pi to Pj, then all the connecting wires between Pi and Pj, or all the connecting paths between Pi and Pj will forward the value to all these channels, and majority of the value will be taken into account at the receiver. Okay, so this is about perfectly secure BA protocol over incomplete graph. Next we moved to one error correcting code. So we will use the error correcting code in design of protocol afterwards, but we introduce the Reed-Solomon error correcting code here. Okay. So what happens here is that you have data word. So error correcting code has the sole objective of retrieving correct data from erroneous communicated terms. So your data word is first encoded to a code word. So this basically introduces redundancy. What we mean by that is, your data word may contain only k elements from some field f, and when you convert it to a code word by the encoding mechanism, it maps to n number of field elements. So of course k is lesser than n, so smaller number of bits are mapped to larger number of bits by the introduction of some redundancy through the encoding mechanism. Now this code word is conveyed through some communication channel, noisy communication channel, and while getting communicated, some noise is introduced and your received code word is a erroneous. So your received code word is an erroneous code word which after decoding will get you back the correct data word. So the received code word can be different from the actual code word. It is still element of f to the power n, but the contents can get modified at some specific index positions, but still so the count of ci not equal to ci dash should be upper bounded by t for a t bit or t error correcting code, right? This is the whole purpose of error correcting code. Now in Reed-Solomon code, basically if this is your message, how do you encode? You construct a message polynomial in this manner. So coefficients of your message elements are basically coefficients of the polynomial, k minus 1 degree polynomial. Now there are some n publicly known values, right? And you basically evaluate your message encoding polynomial at those values. This you want to see in the encoded value or code word. Now after they are received in the receiver's end, so you have received some n number of values, right? So we denote with Rx, received polynomial. Okay. It is some polynomial, say f dash, which has this property, right? F dash alpha 2 is c2 dash. So these are the received values. Okay. So let me denote code word is this notation, and they differ at most t positions. This is the received polynomial, and you also denote with ex the error polynomial. So ex is nothing but x minus u1 till x minus ut. Since there are at most t positions where errors can occur, so let's say C3 is a error position, Cn minus 1 is a error position. Then basically E1 to Et, all of them actually belong to alpha 1 to alpha n, any t positions among these n positions. And this is noticed that this condition is so I can write R only instead of plus instead of plus. Now for positions I, where Ci is equal to Ci dash, there Fm of x and R of x is same, right? Because the corresponding Ci value is unaffected and Ex is anyway same for same value of x, so this condition is satisfied. And if for some I, Ci is not equal to Ci dash, in that case E of alpha I is actually 0 because of the way this polynomial is defined. So in that case both the side will give us 0. So basically this condition is satisfied for all the values I equal to 1 to n, right? And this equation or this function has k minus 1 unknowns starting from m0 to mk minus 1. This has t number of unknowns starting from e1 to ut, which are elements of alpha 1 to alpha n. This is a known polynomial for which you know the n number of points and their corresponding evaluations, so one can get the polynomial Rx, and Ex again is a polynomial with t unknowns. So in general for alpha 1 to alpha n you will get system of n equations, and the number of unknowns are k minus 1 t t. So that is the degree of the polynomials, and number of unknowns is also k plus 2t, which is less equal to n because at starting we assume n minus k is greater equal to 2t. Only then decoding is possible, and since this is satisfied we have sufficient number of equations in our system of equation, and we can solve for the values of these variables, right? And we can recover the correct data work in this. So this was the brief idea on Reed-Solomon code, and then we quickly get an overview of PSMT or perfectly secure message transmission. So previously when we discussed about communicating between sender and receiver over an incomplete graph, so there we actually got introduced in the lecture with PRMT protocol, perfectly reliable message transmission, and here we will talk about PSMT, perfectly secure message transmission. So PRMT, when added with the context of privacy, gives PSMT, right? So if there is a sender and there is a receiver and there is node disjoin paths between them. Now at most t of them can be under adversarial control, and we want that even after having control on t number of wires, the adversary should not be able to know the value communicated between S and R by looking at those t wires. So in the lecture it is seen, it has been shown that for one round PSMT protocol, we need that n should be greater than 3t, and we need that the content of n minus 2t wires needs to be dependent on the transmitted message. Otherwise, correctness, that is retrieval of message by R is affected. R cannot retrieve the message without ambiguity if this is not satisfied, and here if n is less equal to 3t, then security is affected. That means by looking at t wires, the adversary will be aware of the exact message being communicated. Whereas in case of multi-round PSMT, we just require n greater than 2t. So in multi-round, the communication cost has increased than single round, but the threshold, corruption threshold has increased, and here we need the content of n minus t wires to depend upon the transmitted message. So this was the overall content for this week. We will see the assignment question and see their detailed solution in the next week. Okay. So thank you for listening.